Hi, fellow seekers. This was probably the hardest year-end list I've ever done. Mostly because 2021 wasn't a particularly notable year in astronomy. Not that things weren't discovered, of course. It's astronomy. Things are discovered every day. It's just that there really wasn't a story that captured the imagination of humanity. A true wonder to make selection easier. But Nick, you're probably typing now. What about, it? Well, touch meteorite, once it finally gets fully up and running. It's an infrared telescope, so it has to cool down to its operational temperature. We'll start getting a flood of discoveries, which will no doubt form the list for 2022. These lists are getting longer and longer, so I decided to split this one in half. And what better way to begin than with last year's winner? No life in hell, after all. Ah, Venus, for so long you were ignored, the unlovely maiden aunt of the solar system, left to wail of your supposed spinsterhood, the mission schedule for your sulphurous depths as barren as your blasted surface. Except, in 2020, a team at Cardiff University seemingly upended that notion. Utilizing the James Clerk Maxwell Telescope in Hawaii and ALMA in Chile, astronomer Jane Greaves and her team detected evidence of phosphine in your mid-atmosphere. Phosphine, a compound of phosphorus and hydrogen, is so reactive with oxygen that on Earth it is only found in concentrations of parts per trillion. While your atmosphere is not known for its oxygen, it does possess large quantities of carbon monoxide, created by the breaking of carbon dioxide by ultraviolet light from the sun, which can do the job just as well. There is no way that phosphine can remain in your clouds forever. Something must be replenishing it. And on Earth, the only known method, aside from human industry, is life. It appeared you were not so barren after all. Suddenly, we were rummaging through our phones to find your address again. New missions to your fiery, misty realm were moved to the front of the line. For once, Mars was left to stew in your shadow. Except that it again appears that I may have to retract my top choice for a previous end-of-year list, because multiple studies this year have suggested you may be defiantly reclaiming your infertility. In January, a team at the University of Washington constructed a model, a robust model, they assure us, that suggested that the supposed phosphine was naught but mere sulfur dioxide, hardly a square peg in the hellish environs of Venus. The error resulted, the opposing team argue, from the fact that phosphine and sulfur dioxide emit very similar absorption lines in radio light, overlapping at 266.94 gigahertz. How could an experienced team of highly regarded astrophysicists have missed something so mind-bendingly obvious? Well, in fairness, they wouldn't have been able to publish their results at all if they not at least addressed that issue. They first made their detection in 2017, but held it back until they had cross-checked the result with ALMA. Their conclusion was that there wasn't enough sulfur dioxide in Venus's atmosphere to account for such a strong signal. Except, the Washington team assert, at the time of the detection in March 2019, ALMA's antenna was so configured as to fall prey to a phenomenon called spectral line dilution, which causes actually plentiful compounds to emit far weaker signals than their abundance should imply. Of course, the Cardiff team have come out swinging and argue that, leaving ALMA aside, the presence of so many other sulfur dioxide indicators in the initial James Clerk Maxwell Telescope result showed adequately the levels of sulfur dioxide were too weak to produce the signal they saw. The Washington team countered that, according to their model, the signal was detected not in Venus's cloud layers, but 50 kilometers above them, an altitude that would see the sun destroy phosphine in seconds. Basically, as with much astronomy, it boils down to interpretation. More direct results will have to await the arrival of the next fleet of Venus-bound probes, expected to launch over the next decade. And speaking of probes, in March, an archival study by Rakesh Moghul, a professor of biochemistry at California Polytechnic University, may have uncovered evidence of this controversial phosphine from the results of the Pioneer Venus multiprobe, which arrived at Venus in 1978. Mogul had realized that the published data from the probe had focused on the overall composition of Venus's atmosphere and ignored any evidence of trace gases. After chipping meaning from the stream of often context-free data, a feat of translation that would do Champollion proud, he detected what he could only describe as phosphine in the mid-layers of Venus's atmosphere. No other phosphorus chemicals fit the data as well as phosphine, he said in a press release, especially when considering the mild temperatures and pressures in the middle clouds, where many phosphorus species would not be gases. In what may be an even more exhilarating result, Mogul argues that the data also suggests that the chemical composition of Venus's atmosphere is unstable and in a constant state of change, much like our own atmosphere, thanks to the presence of life. But because no parades can remain unrained on, other papers have argued that even if the phosphine detection is real, it still isn't a definitive sign of life. Instead, they argue that the phosphine may be a sign of another aspect of Venus that she has long kept beneath her cloak: active volcanism. In July, a team at the Carl Sagan Institute presented a model that suggested that, provided Venus had a volcanic rate similar to Earth, eruptions could produce enough phosphides to leave detectable amounts of phosphine in the atmosphere once they had reacted with sulfuric acid. While active volcanism has yet to be detected on Venus, in August, researchers Megan Russell and Katherine Johnson of the Planetary Science Institute remastered 30-year-old image data from Magellan, the last time anyone had mapped Venus's surface, to see if they could locate any evidence for geologically recent volcanic events. Aramaiti Corona, a 350-kilometer-wide mountain near Venus's equator that resembles a failed souffle, is obviously volcanic in origin, but precisely how recent that origin is has remained elusive. Russell and Johnson employed a computer model to estimate its age via the amount and form of crustal deformation beneath it, and concluded that it must have been active at least within the last few tens of millions of years. In December, an international team reviewed data from ESA's Venus Express mission, which found possible lava flows around the volcano Idun Mons, and modeled how quickly such flows would erode to nothing in Venus's vitriolic atmosphere. The answer? Within 1,000 years. According to their paper, for the flows to still be extant today, they must form part of an ongoing eruptive cycle. And finally, there is Martin Turbot and his team at the University of Geneva, who in October decided to strip us of our last remaining shreds of hope. The team employed a massive computer program to model Venus's climate over the course of 4 billion years, and found that, contrary to many optimistic models in the past, Venus could never have had an ocean. The model found that water vapor tended to form clouds on Venus's night side, which increased the greenhouse effect above that required for water to condense. The model also suggested that, had the sun been as bright at the solar system's birth as it is now, a similar fate would have befallen the Earth. Personally, I still have faith. Venus's millennia of deceptions and evasions have shown that our solar system's dark lady cannot be truly understood from Earth. Venus girds her petticoats well, and no amount of models, telescopes, and data crunching will change that. Until we arrive there properly attired, Venus will remain her circumspect self. The buzz about Mars. With Venus retreating behind her veils, Mars once again took the spotlight as our world's favorite neighbor. How much do we love Mars? We currently have 13 active probes eyeing its dusty face, including 3 rovers, 1 lander, and 8 orbiters, one of which has been in orbit for 20 years. But this year belonged to the 13th probe, even though, by any rational metric, it hasn't actually discovered anything. Tucked into the automated camper van that is the Perseverance rover, the Ingenuity helicopter was little more than a tech demo, a proof of concept for later, more ambitious missions, such as the Titan Dragonfly mission, scheduled to launch in 2027. The mere fact that the human race now possesses video, and for the first time, audio, of a human-made craft flying through the atmosphere of another world, an atmosphere, mind you, less than 1% as dense as Earth's, calibrated for a different gravity, and conducted essentially blind, as the sluggish speed of light meant that any commands took 13 minutes to be inputted and a further 13 to be acknowledged, was discovery enough. That we can now listen to the meager winds of this ancient desert world could also be worth the effort. That said, the main rover, Perseverance, did manage to make some actual discoveries in the year it has been trundling the dunes. For instance, in September, Perseverance drilled 2 core samples out of the floor of Jezero crater, the bed of an eons-dry lake near Mars's equator, and stored them within itself in the hopes of a future sample return. The rock samples proved to be basaltic, likely from ancient lava flows, rather than sedimentary, as had been expected and hoped. But, excitingly, they also showed signs of persistent, repeated interactions with groundwater. Additionally, studies of the surrounding strata excavated by the impact show several layers of sediment buildup, showing that, far from a meager temporary pond, this crater's lake existed for thousands, possibly millions of years. December saw the announcement of another enticing discovery. Using Perseverance's scanning habitable environments with Raman and luminescence for organics and chemicals, or SHERLOC, the team detected the presence of organic chemicals on the floor of Jezero crater. While this is not a groundbreaking discovery, both Curiosity and ESA's Mars Express orbiter have made similar detections. SHERLOC has the ability to place the organic compounds in their mineral context, opening the window to the environment in which they formed. Future studies could very well provide clues as to in what, and possibly whom, that organic material originated. Not that Curiosity, Perseverance's older sibling, has been idle. In April, a paper in Geology announced that the redoubtable rover had mapped the strata lining Gale crater, its home and work site for the past decade. Curiosity found that the strata overlaid a base of 3.8 billion-year-old clay, indicating long-standing water, with sandstone, indicating millennia of extreme aridity. Patterns within the stone suggest the sand that formed it had had time to accumulate into vast dunes. But above those, Curiosity found alternating beds of first brittle and then hard rock, typical of river floodplains. This indicates that Mars's shift from its early watery environs to its current frigid desert did not happen all at once, but gradually and over the course of millions of years. In January, scientists at Rice University examined Curiosity's data and found, much to their surprise, that weathering of surface rocks on Mars appears to have ended about 3 billion years ago, and that the closest analog on Earth to the features Curiosity found in Gale crater would be a cold, temperate region of relatively young volcanic origin, such as Iceland. But this study was complicated in November when NASA's InSight lander, a probe launched in 2018 that employs Mars quakes to map the planet's interior, detected not only the expected lava flows, but also, between them, lighter layers of sedimentary rock, indicating that Mars has alternated between volcanic formation and climatic deposition over the course of millions of years. And here I must again offer a partial retraction. In my 2018 list, I included the discovery of liquid standing water under the surface of Mars. Unfortunately, 3 papers published in July have suggested that, rather than water, clay might have been the source of the signal. Subsequent observations showed nearly identical signals near Mars's polar cap originate far closer to the surface, where temperatures are too cold for liquid water to exist. A number of materials, including metals and saline ice, could be producing the signal, but a study in a liquid nitrogen-cooled lab on Earth have pinpointed a possible culprit: smectite, And no, I did not make that word up. Derived from the Greek for smeared, smectites are a type of clay that expands when soaked in water. In fact, studies show that smectites may be where most of Mars's water went. Smectites can be stable at up to 600 degrees Celsius, which would be below 30 kilometers depth on Mars. If you recall from my water series, I explained that water with a higher deuterium content, or hydrogen with an extra neutron, indicates that it was once present in greater abundance. The higher the ratio of deuterium to normal water, the higher the initial amount. The study suggested that the deuterium ratio in Mars's water cannot be explained solely by water escaping Mars's atmosphere, and instead must have been aided by sequestering within Mars's crust. On Earth, such water is recycled to the surface by volcanic and tectonic activity. On Mars, such activity is rare to non-existent, and water remains forever trapped in smectite. That sounded more obscene than I intended. It seems that after Venus stole his thunder last year, Mars is determined to remind us that he is still Earth's favored sibling. Here's hoping he's as outgoing if and when we finally arrive in person. Where the black planets roll without aim. Our universe is night eternal. Only by the grace of our meager and mortal sun does our species even comprehend the light of day. And yet in our search for other worlds like our own, our eyes have gazed upon worlds forsaken, abandoned to the night, as we know ours will one day be. The first glimpse came in 1992, when the first exoplanets ever discovered staggered the world by circling a pulsar, the black corpse of a gigantic star that ended its life in a supernova. Such planets must have reformed from the wreckage of their dead star's first children. Since then, tenebrous planets have been found around many stellar corpses, including not only pulsars, but white dwarfs. In fact, we found one this year, which, in an eerie vision of our own solar system's future, is roughly the size and distance of Jupiter. And even, potentially, black holes. A so-called blanet has yet to be detected, though models suggest they are at least possible. But the true forsaken of our galaxy are rogue planets. Those worlds stripped of their parent stars and left to wander the black chasms between the distant huddled fires. Detecting such objects is not a simple task, not because they are difficult to find, but because, as of now, we still cannot say what a rogue planet even is. Just as Pluto and Eris have sparked confusion about the point at which an object becomes a planet, so the various candidate rogue planets have sparked confusion about the point at which it ceases to be one. Astronomers employ the term brown dwarf to describe an object too large to be a planet, but too small to fuse hydrogen. The traditional cutoff points for brown dwarfhood are 75 Jupiter masses at the top and 13 Jupiter masses at the bottom. Why 13 Jupiter masses? Because at that point the object can fuse deuterium, which, because deuterium is about 10,000 times rarer than hydrogen, it can for just 100 million years. If that cutoff seems arbitrary to you, you're not wrong. There is no reason, after all, that an object smaller than 13 Jupiter masses can't form from the condensation of a nebula, so-called core collapse, just as a star does. If it formed as a star, is made of the same stuff as a star, and perhaps even has the planets of a star, can it not be a star? Well, no. Given the wretched state of our understanding vis-à-vis the formation of planets versus stars, all we can do is plaster the name planet on anything that fits the mass criterion, regardless of how it formed. And given that determining the mass of an object that isn't orbited by something else is usually impossible, that number of confirmed rogue planets to date is understandably minute. The best candidates found so far have been from microlensing events, fleeting moments when a shadowy massive object passes in front of a light source, briefly bending it. Since the duration of the bending is determined by the mass of the object, it has provided to date the best option for securing rogue planets. But there's a problem. Science relies on repetition. You can't declare a discovery a fact until someone else independently confirms it. And microlensing events only happen once. One way to confirm a rogue planet would be to observe a lot of them. If you can find a large enough sample, then by the application of some hardcore statistical techniques, you can winnow it down to some pretty solid possible. And in December, a team led by Hervé Bouy, an astronomer at the Laboratoire d'Astrophysique de Bordeaux, announced in the journal Nature that it had identified the largest single cache of rogue planets ever found. From a combination of new observations and the search of 20 years of archives, the team scoured the over 4,000 possibilities to find 70 reasonably certain candidates. The trove lay in the Scorpius-Centaurus Association, a relatively nearby group of young co-moving stars, including the red supergiant Antares. Their youth was a valuable asset for the searchers, as any rogue planets, or sub-brown dwarfs, would still be cooling from their formation, and were thus far brighter. The ultimate conclusion of this search was that there were far too many rogue planets for core collapse to have been their only origin. Some must have undergone the trauma of existence in the nightmare of space, perhaps ejected from their hearth before they could be fully born, or blasted down to nothing by the rage of nearby supergiants. Eventually, these true wanderers will fade and drift the cold depths of the night, even after the last fires have gone out. And they weren't the only ghoulish discovery made this year. In February, it was announced that white dwarfs contained elements in their atmospheres in ratios eerily similar to those found in terrestrial planets, in amounts comparable to a large asteroid. One of the white dwarfs was perhaps 12 billion years old as the Milky Way itself. Because the material most closely matches that seen in planetary crusts, it seems that whatever that white dwarf had consumed had once been a fully formed planet. Additionally, an infrared excess was detected around the dead star, suggesting it was surrounded by a debris disk analogous to our asteroid belt. The black, jagged remnants of a planet long broken, orbiting the corpse of a star long dead. And in November, a separate team analyzing, quote, pollution in similar white dwarfs came to a shocking conclusion. Some of these corpse worlds were unlike anything we have seen. In fact, so alien was their composition that the team had to invent new classes of rock, such as quartz pyroxenites and periclase dunites, to explain what their original forms must have been. Unlike the previous study, it appears whatever this star had smeared over its face was more akin to mantle than crust, suggesting these rocks had formed deep within their planet. One wonders what strange forms ambled across those ancient alien landscapes. Relax, we're normal. In my previous year-end list, I noted that the cosmological principle, the idea that we should not consider our position in the universe to be special, had calcified to the point of dogma. Evidence, particularly on the universal scale, was increasingly suggesting that our position within it was not, in fact, normal, but very specific. But I still hold that while it is a lousy creed, the cosmological principle is still a useful assumption to make when confronted with a sample of one. For instance, when I was a kid, extrasolar planets were still the province of science fiction writers, and so, with a sample of one, astronomers assumed that any extrasolar systems we may one day find would follow the rules set down by our own. Small terrestrial planets close in, giant gassy planets farther out, perhaps separated by a ring of debris. Each planet would be slightly farther from the sun than the previous, in a roughly doubling pattern. Then came 1995, and the first extrasolar planet found around a sun-like star. 51 Pegasi b was a fairly standard gas giant, slightly more massive than Saturn, except it orbited its star in just over 4 days. Mercury, the closest star to our sun, orbits in 88 days. How had this benighted world managed to survive billions of years next to a nuclear blast furnace? How had it got there in the first place? Over the following decades, it almost seemed as if the cosmos was making fun of us. Not only had the number of hot Jupiters, as they were called, increased substantially, but an entirely new class of planet, the super-Earth, or mini-Neptune, worlds with masses between 1 and 10 Earth masses, proved to be the most common type of planet in our galaxy, even outnumbering terrestrial planets. And we didn't have one. When the Kepler satellite got our first seemingly representative sample of extrasolar systems, we appeared to be the one begging the bouncer to get in the club. Other solar systems had worlds all roughly the same size and equally spaced. Our solar system, apparently, was a lopsided freak. After 25 years of contrary results, perhaps it was time to ditch the cosmological principle and call in the anthropic. Could our solar system be weird because we're in it? Could there be something about our solar system's oddball evolution that was vital to the development of life? Problem was, no one could figure out what that could possibly be. But even after 25 years, we can still fall prey to sampling error. And last year, astronomer Wei Zhu of the University of Toronto argued that's exactly what we did. The supposed identikit solar systems observed by Kepler were, he said, due to statistical noise in the stellar activity that interfered with the transit data. And this year, with the conclusion of a 30-year survey, a California-based team of over 20 astronomers apparently confirmed that assertion. No need for existential pondering. It appears our solar system is normal after all. The team conducted a radial velocity survey of over 7,000 stars, monitoring them for the wobbles caused by the gravity of orbiting planets. The decades-long duration of the survey allowed them to catch wobbles from distant gas giants more similar to those in our solar system. Radial velocity isn't suitable for detecting small planets like Earth, but the masses measured covered a vast range, from 3 times the mass of the Earth to 20 times the mass of Jupiter, more typical of a brown dwarf. The survey was able to show that of the 177 giant exoplanets identified, the majority seemed to cluster between 3 and 10 AU, exactly where we would expect them to be if we were looking for cousins of our own solar system. If the data hold true, then we should expect about 14% of star systems in our galaxy to resemble our own, or about 1 in 7, a perfectly comfortable ratio. Hot Jupiters, once so prevalent in our surveys, proved to be surprisingly rare, while giant planets in the region of Uranus and Neptune appeared less common than would be expected from our system. Though that might be an artifact of the duration of the study, and 100 to 200-year studies might be required to find all of them. The last few decades of astronomical exploration have forced us to ask some fairly difficult questions about our place in the universe. We can take heart in the fact that as of 2021, we now have one less. Exoplanet excitations. Another year, another list of exoplanet firsts. Sadly, still no winner of the Triple Crown, Earth-sized, water in the habitable zone. But that might change soon if a certain something does as well as it looks like it might. Also, while they don't exactly count as discoveries, 2 studies released this year have suggested that watery Earth-like planets may be far more common than we think. The first, published in February by a team at the University of Copenhagen, showed that, far from due to the random chance of cometary impacts, water may be an intrinsic consequence of terrestrial planet formation. As followers of my water series will know, water is one of the commonest substances in the universe, and often exists bound to particles of interstellar dust. According to the team's models, even during the fiery infernal chaos of planetary accretion, terrestrial planets are able to retain about 0.1% of the water contained in the interstellar dust from which they formed. 0.1% may not seem like a lot, but when you consider that the oceans comprise just 0.05% of the Earth's mass, that's enough to cultivate a verdant paradise 20 times over. The second, a joint study by Stanford and the University of Chicago, suggested that many so-called mini-Neptunes are in fact balls of magma cloaked in atmospheres of hydrogen. The team surmised that these planets exist around young stars, before the magma reacts with the hydrogen to form water. And the maturing sun blasts the remaining hydrogen from its atmosphere as it undergoes the stormy adolescence that plagues all stars. If so, many terrestrial planets would begin life as larger, gas-rich worlds before transforming into their more familiar forms, which would mean water may exist beneath the surface of even the most hostile terrestrial planets. That said, also in February, a study from McGill University suggested that rather than starting big and growing small, mini-Neptunes start small and then gain their atmospheres, just like planets in our system are believed to have done. So, once again, astronomy proves that drawing conclusions from a distance of 500 quadrillion kilometers is bound to leave room for interpretation. As for the actual discoveries this year, we begin with one that, on the face of it, you'd think we would have found by now. HAT P11b is a Neptune-sized planet in a system 123 light-years away that orbits 20 times closer to its star than Earth. This, along with its orientation relative to Earth, made it ideal for detecting transits. After 6 transit observations in the ultraviolet, the team detected a halo of carbon around the planet, implying it possessed something most planets in our solar system do, a magnetosphere. This is the first detection of a magnetosphere in any exoplanet. The carbon ions not only surrounded the planet, but extended outward into a gigantic magnetotail. While it was hardly a surprise that planets outside our system have magnetospheres, given how utterly vital they are for the formation and evolution of life, it's nice to know they're there. There is a pattern in exoplanet detection. Up to about twice the mass of the Sun, the larger a star is, the more likely it is to possess giant planets. That makes sense. Larger stars have larger gravities, and so will attract more circumstellar material, which will then form into larger planets. Except once a star crosses the 2 solar mass line, the number of giant planets in its retinue declines precipitously. That also makes sense. Larger stars, called B and O type stars, have surface temperatures of 30,000 kelvins, which is 5 times that of the Sun, and luminosities 10,000 to 1,000,000 times stronger. This luminosity should heat up and disperse any surrounding gas, leaving no material to form planets. Such stars also live only between 10 and 100 million years, and should be in the advanced stages of death before any planets have had time to establish themselves. Except, in December, a team at Stockholm University snapped an image of a planet orbiting a gargantuan 560 AU from the double star system B Centauri. Not to be confused with Beta Centauri, apparently. The system has a combined mass of 6 to 10 times the mass of the Sun and is the largest structure ever found to be orbited by a planet. Until then, 3 solar masses have been the upper limit for stars hosting planets. The planet is 10 times the mass of Jupiter, nudging brown dwarfhood, and with an eccentricity of 0.4 and an inclination of 130 degrees, it whirls around its host star like a bolas. That, together with its insane distance, suggests that the planet was captured from another system, early in its parent star's lives. In October, a team at the University of Nevada announced that they believed they had found the first exoplanet to orbit 3 stars. This circumtrinary planet, my source uses the term circumtriple, but I won't, was inferred from a gap in the dust disk around GW Orionis, a triplet system of young, violent stars all about the size of our Sun. The disk is one of the largest ever discovered, with a radius of up to 400 AU and a mass of 487 Earth masses, or about the combined mass of our own planetary system. This world is likely a gas giant, as theory says they are the first planets to form. Nothing else is certain about it, even if it exists, but if it does, it has a killer tourism industry in its future. In 2019, an exoplanet discovery occurred that really should have made my list. HD 3167, an orange star about 150 light-years away, was already known to have 2 transiting planets, but subsequent transit observations showed that at least one of these planets was orbiting at a nearly polar inclination, at right angles to both the inner planet and the plane of its star. A third planet was eventually found to be doing the same thing, leading to the obvious question, why? Planets' orbits are not known for flipping sideways, and that planets orbit in the planes of their stars is kind of fundamental to our theories of solar system formation, so this needed explaining. When something bizarre happens to a planet, the usual suspect is another planet. And in October this year, a team at the University of Geneva, employing more precise data, concluded that the innermost planet's proximity to its star allowed it to retain its planar orbit, while the two outer planets were yanked into their oddball orbits by an as-yet unseen companion. So, we meet again, science. Just as I was about to finally put one of my more difficult audio recordings to bed, I'm still getting used to my new microphone, I learned that there has been a new development in a particular system about which I have taken upon myself the responsibility to report. Not world-shaking news, it must be said, but worth inclusion nonetheless. Accepted on December 21st, and thus just making it under the wire, a paper published by a team at the European Southern Observatory confirmed, via the redoubtable espresso machine, what had been hinted in the data confirming the existence of Proxima b in 2020. That another planet existed closer in. This world, Proxima d, planets are listed in order of discovery, not distance from their stars, is smaller than Proxima c. According to its discovery paper, it possesses roughly 1 Earth mass, though an earlier estimate in 2020 suggested at least a quarter Earth mass. It has an orbital period of about 5.12 days, which would grant it a semi-major axis of 0.029 AU, and an orbital ratio with Proxima b of 0.6, compared to 0.7 for Earth and Venus, and 0.4 for Earth and Mercury. That does not bode well for habitability, and indeed, making the very safe assumption that it is tide-locked, and granting it an Earth-like albedo of around 0.25, its temperature, if it lacks an atmosphere, which, let's be honest, given its proximity to a raging baby like Proxima, it almost certainly does, would be 490 kelvins, which is about 212 Celsius. Not exactly homey. Although, if it had an albedo of 0.8, equivalent to fresh snow, I don't know, maybe it's covered in chalk or something, it would have a surface temperature of 290 kelvins, which is about the same as Earth's. It probably doesn't. And that's the first half. Hope you find it interesting and don't mind the wait. But if you do, please tell me in the comments, and we'll try it again next year. If you're new here, please may you like, comment, and subscribe and all that good stuff. I read every comment, and I'm grateful for every view. And I hope to see you again next time.